Hello, our experiment is about the band gap energy of a semiconductor. So obviously our aim is to determine the band gap energy of the semiconductor. In this case we use germanium as a semiconductor. Now coming to the theory, semiconductors are the materials that conduct in between conductors and non-conductors. Non-conductors means insulators. The band gap energy is the minimum energy that is required by the electron to move from its bound state into a free state where it can participate in conduction. The lower energy level of the semiconductor is known as the valence band, and the higher energy level is known as the conduction band, where the electrons will be free. So the gap in band gap is the gap in energy between the bound state, that is between the valence band and the free state. Free state means the conduction band. So once the electron gets excited to the conduction band, it is completely free and thus it can participate in conduction. According to the band theory, semiconductors will act as insulators at absolute zero temperature. Above this temperature and below the melting point of the material, the metal would act as a semiconductor. We know that insulators have a very large difference in the band gap, that is there is a large difference between the valence band and the conduction band, and hence the electrons that are present in the valence band cannot move to the conduction band. The valence band will be completely full and the conduction band will be void of any electrons. Therefore the insulators cannot conduct, or the electrons in the valence band cannot move to the conduction band and will not be able to participate in conduction. In the case of the experiment, we used a point contact diode OA79. It can be conveniently used to determine the energy gap of a semiconducting material. In the reverse bias condition, the current flowing through the junction will be very small and the internal heating of the junction does not take place. As the internal temperature increases, there will be increase in thermal energy, and this creates vibrations in the lattice. The electrons that acquire sufficient vibrational energy will break their covalent bonds and become free, and hence they will move to the conduction band. So we can define the energy that is required for an electron to reach the conduction band from the valence band is known as the band gap energy. We have the equation for the reverse saturation current of the diode given by I is equal to A exponential minus Eg by kT. Here A is a constant, Eg is the band gap energy, K is the Boltzmann constant given by 1.38 into 10 raised to minus 23 joule per Kelvin, and T is the absolute temperature. Now taking log on both sides of the equation, we get log I is equal to log A minus Eg by kT, or log to the base 10 I is equal to log to the base 10 A minus Eg by 2.303 kT. Now we plot a graph between log to the base 10 I and 1 by t, which will give a straight line, and the slope of this straight line is given by Eg by 2.303 into K. The band gap energy Eg can be given by Eg equal to 2.303 K into slope. Therefore, we can calculate the band gap energy of the semiconductor by first drawing the graph between log to the base 10 I and 1 by t, and then finding the slope from that graph and substituting in the equation for band gap energy. This is the circuit diagram and the sample graph that we will obtain while doing the experiment. Now the procedure for the experiment is, first of all, do the connection as shown in the figure. Then the diode is kept in the reverse bias condition and it is immersed in a paraffin wax bath. This paraffin wax is taken inside a test tube, and this arrangement is completely dipped inside a beaker that contains water, and it will be heated. Also a thermometer is kept inside the paraffin bath in order to get the corresponding temperature. Then we note the reverse currents at various temperature by keeping the voltage across the diode a constant value. After that, we will plot the graph with 1 by t along the x-axis and log to the base 10 I along the y-axis. Then the slope of the graph is calculated. Then the band gap energy is calculated by putting the slope in the equation, Eg equal to 2.303 k into slope. Then this experiment will be repeated for different value of voltage across the diode, and the band gap energy is calculated. Our expected result will be in the range of the band gap energy of the semiconductor. Here we have taken germanium as a semiconductor. We know that the band gap energy of germanium is in the range of 0.7 electron volt. Therefore, from this experiment we will have to obtain a result that is close to this value. Thank you.